Good morning, good afternoon, good evening, everyone, and welcome to episode number 148. We're going to explore some kind of advanced functionality of Cilium today. We're going to talk about what the use case is and how all of it works. Should be super fun. I'm glad you're here. If you are here, throw a note in the comments. Let me know where you're from. Be awesome to see everyone. All right, get my screen presented here. Entire screen, gonna go with that one. All right, first things first, let's go ahead and get started with the news. Announcements are almost out for KubeCon, not quite out yet, but real soon here. And then we're also going to see the opening of the CFP for rejects in Salt Lake City, Utah. So I hope that if you have submitted a talk, that you get it accepted. And if not, then you will know soon, as will I. So I'm excited about that. Let's see, we got the newsletter for the day coming up. Episode number 61 of the newsletter came out July 30th. Like all tech newsletter, it's time to add my commentary to the CrowdStrike incident that crashed IT systems around the world. That was wild. Absolutely wild. But there's lots of great stuff in here, including a live migrating production clusters from Calico to Cilium, talking about how the different methods and the different ways and the different concerns around it. We've actually done some talks around this ourselves, or I've done some talks around this myself and actually showed you how to do that with Multis and with a variety of different ways. Honestly, whenever you're switching out a CNI, though, it is best just to replace the cluster with the new CNI rather than trying to actually manage the scenario where you have to migrate from them, because that's going to leave you in the cleanest state throughout. We have eBPF application written in pure Java. Wild. We have making a damn vulnerable web application almost unhackable with Cilium and Tetragon. I like that. Basically showing where we can add defense for known vulnerable things. Uses eBPF to monitor and dynamically adjust traffic speeds to gently nudge users off configured sites. Interesting. I don't know what that does. We got the 1.16 release. Just last week, we had the European version of that. And the week before that, we had the American version of that, where we actually had some of our awesome contributors and maintainers live on the session, talking through how it all went. Lots of really great stuff coming out in 1.16, including port ranges, which has been a long time coming. So that's now in the 1.16 release. And we also have just a variety of other really great stuff, including we're continuing to advance in the Gateway API space. Lots of really great stuff. In the ecosystem, obviously lots of stuff about CloudStrike, because this was a little while ago that it came out. But there's a really great chat with Alex Williams and Thomas Graf talking through Cilium and what's happening at Isovalent and what's happening with the future of the product line, etc. So I think that's going to be a really great article. If you haven't checked it out, I definitely recommend you do. Cilium for AI ML workloads, eBPF use cases, architecting cloud-native platforms, the role of domain-driven design and cell-based architecture, and the role that network policies play. I like that. The how-to, talking about Cilium service mesh on EKS, enabling enterprise features for Cilium in EKS, and Cilium on EKS with Speltos. So lots of EKS articles, install Cilium in WSL2, interesting. EKS and Isovalent for Cilium, reducing operational complexity. Get into the events. We just did these two events, the intros to networking security and SecOps and the networking security zero trust visibility event. Hope you attended, and I hope you got into the raffle. Coming up on September 11th, not very far away at all, we're going to be hosting the eBPF Summit again, and we are reviewing the proposal now. It should be a really great virtual event. I'll be one of your hosts, along with Liz Rice. So excited about that. Is there a Cilium for Dummies that would explain Cilium to me and how it works? Well, there is kind of that. Let me show you where that is so that you can actually get started here. So if you go to isovalent.com/labs, the labs here are quite extensive, and they give you a pretty good overview of how all of it works. You can also, for an overview, go to docs.isurveillant.com, and it will take you through like the different solutions that are out there. If you want to know about Cilium, you can click on Cilium. It'll talk you through like what it is. There are tutorials, there's documentation, there's lots of really great stuff to kind of get started here. Okay. What else do we have here? Tetragon Cloud Native Security Workshop. Like I said, and then we also have an eBPF and Cilium Day in Salt Lake. That'll be exciting. All right. Okay, well, let's get started with the actual fun part of our show, in my opinion. So today we're going to get pretty hands-on and pretty technical. So strap in. It's going to be a wild one, but I kind of want to talk through a couple of different scenarios here and help explain like why this is such an interesting thing. We're going to start a little bit with just Kubernetes services. We're going to start a little bit with Kubernetes services and how they and where the enforcement point for network policy is. Now, I think probably because I've been doing it for so long, it's kind of obvious to me that network security policy applies at the workload. When you write a network security policy for a Kubernetes workload, then the place where that gets enforced is on the workload itself, right? Or traffic coming into or out of the network namespace that the application that you've deployed is in. So if you deploy a web server and you write network policy, then the network policy will affect traffic coming in or leaving the web server that you've deployed inside of Kubernetes. The interesting challenge, though, is when it comes to being able to enforce traffic from external sources. If you have traffic that's coming from outside the cluster, or in most cases with the CNI, if you have traffic that's coming from other workloads, but trying to limit things by IP address, then the assumption is that the IP address will be known when the traffic arrives at the workload. And in reality, that's not the case for a variety of really interesting reasons. And we're going to kind of dig into this a little bit. But as an example of this is the Kubernetes service of type load balancer or service of type node port example. If you were to go ahead and expose that web server that you created via a service of type load balancer, and then you routed traffic to it from the outside world, which is kind of the whole point of having a service of type load balancer, then what ends up happening is, depending on how that load balancer is configured, that traffic may land on a workload, on a node where the workload resides, and thus the source IP address is kept, or it could land on a workload where it could land on a node where the workload does not reside, and basically kubeproxy or some other mechanism will route the traffic over to a node where the workload resides, and that routing step basically means that you lose the source address, because now the source address is whatever that intermediate hop is. That's an interesting piece, because it means that if you were trying to write network policy that says, I want to limit traffic from the outside world into this web server, but I'm going to expose this web server via a service of type load balancer, then I have to have some means of guaranteeing that the source address is not lost, or that I can implement network policy at a different enforcement point to ensure that traffic coming in via service like load balancer is considered when traffic is being enforced. So let's do a bit of a hands-on demonstration of that, shall we? All right. Let's throw my screen back up here. You should be able to see my, go ahead and ditch this little cluster that I created. Cluster. And I'm going to go into, let's see that. Now, I'm doing a couple of different things here. One thing I'm going to do is I'm going to bring up a container lab, because I want to expose my services of type load balancer via BGP. So I have different sources, and I can kind of control about how it works. All right, so let's take a look at my container lab topology. So this is the container lab topology that I'm going to be using for this. And what it's going to do is it's going to create a router in the form of a container running inside of my laptop. And then I'm going to configure that router because it's basically the router, the core router. I'm going to go ahead and allow things to masquerade out the eCHO interface of that router. And then I'm going to go ahead and configure the rest of this particular router, which is basically allowing for there to be a peer group. I'm going to allow net 0 to interface with other routers, and the same thing with net 1. And then down below, I've got my TORs. So they're going to basically auto register, and they're going to redistribute anything connected to itself and also to the TORs that they learned from. And then I have my TORs down below. I'm adding some IP addresses to interfaces. The TORs are broken across the idea that there is a connection going to the core router. There's a connection going to each of the 2 different network interfaces, and that will connect us to the actual interfaces on the kind cluster that we're going to create. So we're going to create a 4-node cluster. TOR 1 and TOR 0 is going to have connections to the first 2, the control plane and worker, and this TOR 1 is going to be connected to the second 2, worker 2 and worker 3. And each of them is going to be basically peering with that router at the top. Inside of the configuration of the container lab, they now have a resource called K8's kind. So you can actually just pass the configuration of a kind cluster right into here. And so I thought that was pretty cool. That's in here, and I'm making use of it. Now, the other thing I'm going to actually do is I'm going to go ahead and map the other side of the connection for each of my kind nodes into the TOR that they're connecting to. And I'm going to replace the default route with its connection to that TOR. So that means that although it is a kind cluster and it's configured to connect to everything in the kind network, what I'm going to be doing is actually changing the IP address of the node and wiring it up so that it's like a direct one-to-one connection with the TOR, and sending all traffic from that node out over that TOR instead of routing over the existing kind network that I'm connecting to. So it's a little bit of an advanced configuration, but that's how we're doing it. And then in the links here is how I'm wiring everything up, right? So router 0 net 0 is connected to TOR net 0, router 0 net 1 connected to TOR 1 net 0, TOR net 1 connected to lab control plane. That's what we were talking about. And then net 2 is connected to lab worker. Lab worker 2 and lab worker 3 are connected to TOR 1. All right. And then the cluster configuration, what I'm doing here is I'm actually, I'm configuring a pod subnet. That'll be the 10.100/16. That's outside of the range that I'm actually deploying for the rest of the nodes. And then in the node IP field of the kubelet extra args, I'm actually going to specify the IP address that the node will know about. And then I'm also adding some labels, rack 0 and rack 1. And we'll talk about why I'm doing that here in a second. So that's the overall topology we're going to be deploying. Let's go ahead and get that deployed. I have this make file that I've created. And when what we're going to do is we're going to enable BGP control plane. We're going to enable BPF masquerade. We don't need egress gateway. We're going to separate the envoy out to a different daemon set. We're going to use gateway API. We're going to enable gateway API. We're going to enable Hubble and Hubble relay. We're going to, I forgot to enable Hubble UI. Set Hubble UI enabled equals true. Okay, we're going to enable Hubble UI. We're going to enable the ingress controller, and we're going to do these 2 pieces here, these 3 pieces down here, and this is a very important piece. We're going to talk about why. But I think if I do this now, it's going to show you how it works without actually showing you how it breaks. So to that end, I'm going to comment this out. And we will look into why Geneve is necessary first. And then we'll apply it. All right. So the next thing, actually, you know what? I guess what I just need to do is get rid of this part. We can leave the protocol Geneve. All right. So the next thing we're going to do is we're going to wait for the LVI pool, load balancer IP pools to exist. So let's go ahead and get this started up. So let's do make up. That's going to create our container lab and wire things up as we talked about. So Geneve and VXLAN. So by default, Cilium actually deploys using VXLAN. And there's a great article I found on IP with Ease. It's a blog that actually describes like the difference between the two and what they're used for. Although VXLAN, as defined in most places where you will see it defined, includes a different type of topology than we're using VXLAN for, right? We're using VXLAN simply for encapsulation. And so the VNI here, this field in the VXLAN header, is actually used by us to convey the identity of the workload in the VXLAN header between different nodes if we're encapsulating between nodes. Geneve, on the other hand, has a lot more capability. It has a whole other field here, including option length, that allows us to actually define a lot more information. And we're going to make use of that here in just a minute and show how this works. So Geneve basically enables quite a lot more capability around being able to inject information into what's happening inside the packet. And get cluster. There's something up here. Let me see. Name Cilium. Yes. Looks like it did create it. Lab. All correct. Lab worker 1, lab worker 2, lab worker 3. Let's try this one more time and see what we're missing here. So what should happen is that the cluster should be created, and then we should move on with the rest of the configurations. There's the connections between the labs and the nodes. What was the error? Oh, for cluster name C labs. That's what happened. That's the problem. I have a typo. My typo is right about creating clusters and tearing clusters down is when all you're doing is creating containers. It's just, it's like, and you know why it's so fast, but at the same time, it's still just a surprise every time, All right. There we go. Installing the Gateway API CRDs, installing Cilium. Where's my problem? Oh. One more time. Quick iterations. Waiting for the LBI pool, IB pools to exist. This is a resource of the BGP configuration. So once Cilium gets up and running, you should see that land. There we go. So now we're also adding some Gateway API demo stuff, basically 3 tenants and book info in each one and echo in each one. And that's how we're going to be doing our test. So just deploying a whole bunch of stuff. Okay, and it looks like we have some things mapping in here. Not completely all the way in yet, but we're getting there. We have our 2010 30.0.100 and 40.0. And if I go back to my browser, I should be able to navigate to any of those. So let's say 20.0.10.1. 100. Hello, this is the book applications, a simple simple bookstore application consisting of 3 services as below. So there we go. We can look at it as the normal user. We can interact with it. It's the book application that has been deployed inside of here. And what I'm using to actually connect to it is Gateway API. So let's take a look at our configuration a little bit more. And then we can actually try proving out what we were talking about before. Let's move that. Let's move this to number 3. All right, so you could all edit. Actually, let's do this first. Get pods -n tenant red. So you can see we have an echo service deployed here. So you could all get svc-n tenant red. K S tenant red. All right, so kubectl expose deployment echo type load balancer labels color equals red port 80. All right, so now if I navigate to that, oh, but we don't know what the IP is, so kubectl get svc-n. So we picked 30.0.10.2. And if I navigate to that on port 8080, then I should get the following, which is a map of the echo server IP, or the echo server piece. Now, what's interesting is that I'm coming in from port 10.1.3.2.6. And if I refresh this a few times, might have to do it from the console to really get a good refresh. So let's go back over to 2. Curl minus SSL 30.0.10.2 colon 8080 grep requesting. Well, the source port's changing, but we're not changing IPs. Okay, well, this is interesting, but the 10.1.3.26 address, that's going to actually be one of the nodes that I'm landing on. And because of my routing configuration, currently, I'm actually just using the same route to get to this thing every single time. There's no multiple routes because it's all going to attract me to that one. So if I were to use the Cilium command line tool and do Cilium BGP routes, I can see all the routes that we know about, right? And if I look for the IP address that I'm connected to, which is the 30.0.10.2, I can see that 30.0.10.2 is being attracted to control plane 1. It's being attracted to lab worker. It's being attracted to lab worker 2. And I know that because I can see here, it says the IP address 30.0.10.2, and it's being attracted to 0000, and the next top is 0000. So it's saying, you can send that traffic to me, and I will send it where it needs to go. And that means that the IP address is being lost because I could be landing on any of these nodes, and I promise the echo is only deployed to one of them, right? So if I do kubectl get pods -o wide, you can see that echo is actually deployed to lab worker 2. But I'm attracting that traffic because of the designation of the service to any of the worker nodes. Now there is a workaround here, right? And let's just try this out real quick. So if I edit that service that I created, and I set the external traffic policy to local, what do you think will happen? So now what's happening when I look for 30, 0, 10, 1, or 10, 2, where do I see it? Right? It looks like I only see it on lab worker 2. And when it's being advertised by other nodes, so like in this particular case, it's being advertised by lab control plane and lab worker. So it is actually being attracted to multiple nodes, but every one of those nodes is saying, don't send it to me, send it to 10.0.0.1. Right? And lab worker 2 is saying, if you're going to 30.0.0.2, send it to me. Because lab worker 2 is that IP. So what happens now when I actually run my curl again? So now I'm actually seeing the true source of the IP address, right? The IP address is actually, I'm coming from the 172.20.21 address because that is my connection to the CLab network as defined right there we go. So it's connected as part of the bridge, right? So 172.20.21 is the IP address of the bridge interface. That is that CLab network. And that's where I'm coming from when I make that connection. So whenever I do my curl, I'm always seeing it come back now, even though the IP address has changed or the port's changing, I'm always seeing that traffic come back to the same source address. If I wanted to enforce a network policy for traffic that's coming in from outside the world, right? So let's say I wanted to allow traffic from my own IP and only my own IP. If I apply this -f bmp.yaml, and that's going to apply to any endpoint in this namespace, I should still be able to curl it. That's good. But if I change that service designation again, it will no longer work. So if I do kubectl edit the service and I change that back to cluster, it will work intermittently or not at all. Right? And we know why, because the enforcement point is the workload, right? And when the traffic shows up at the workload, the IP address has changed. Because now the IP address is actually that internal IP. Let's take a look at Hubble and prove that out. So Cilium Hubble port forward. Let's scroll this up a little bit. We'll do Hubble observe -n 10 red -f. Do that again. We can see it's policy denied by drop, and we can see that the reason is because it's coming from the world, and we don't know that IP. That IP is not part of our network policy. right? Interesting stuff. And this is this is a challenge when you're thinking about how do you apply network policy inside of a cluster for things that are coming from outside the cluster. And you need to retain that source address so that you can reasonably enforce it against it. Now, so like I said, one workaround is to change the service to service type um, external traffic policy, or to change the external traffic policy model, right? So let's say I do that. Let's go ahead and change this again. Let's go ahead and make this local one more time. And I'm going to go ahead and scale up the echo service. Now we can see, because we're looking with our eyes here, that echo is deployed inconsistently across the set. There's 2 on worker 2, there's 2 on the lab worker, there's 2 on the lab worker 3, and there's only 1 on lab worker 2. In fact, let's fix this a little bit. So kubectl edit deployment echo. I'm actually going to put a node selector in here. Because I want to force all of these things out of the same node. Name, lab, worker. So now they're all on the same node. And so in this scenario, we would get an even distribution, right? Because what happens is I'll attract that traffic to the same node, and I'll get the same IP every time. So curl minus SSL get SVC 3002 colon 8080 requesting and actually what I want is a different thing. I want the hosting. So we can see that we're actually we're dispersing this traffic across multiple of those same replicas. And partially that's because this traffic is landing on a single node. It's being attracted to a single node, and it's dispersing it across that set. So now if I do my edit again, and I get rid of that node selector, or node name, I should say. And we see our dispersal is back. And now, because of the routing that's happening inside of this scenario, I'm sending all of my traffic to just 2 hosts. Even though there are 5 or 6, all of my traffic is just landing on 2 of them. And part of that is that my routing configuration isn't quite 100%. So that means I'm not doing a true ECMP. It's not equal cost for all things. I'm actually sending it only to the first one that I match on, which is likely to be the lab worker 3, it looks like. It's the path I'm taking. Right? I'm sending all of my traffic just to lab worker 3. Now, there's another way to solve this very same problem, and that's what we're here today to talk about, because what I want is a better dispersal of traffic, but I don't want to lose the IP address. And for that, Cilium implemented a thing called docs.cilium.io. We look at DSR, direct server return. So by default, Cilium eBPF's node port implementation operates in snap mode. That is when node external traffic arrives and the node determines that the backend for the load balancer, node port, or services with external IPs is at a remote node, then the node is redirecting the request to the remote backend on behalf by performing SNAT, source NAT. This does not require any additional MTU changes. The cost is that it replies from the backend need to make the extra hop back to the node to perform reverse SNAT translation and therefore return the packet directly to the external client. This is also true when you're trying to enforce traffic from the outside world, right? So one of the benefits of DSR mode, and another advantage in DSR mode, is that the client's IP address is preserved. So policy can match on it at the backend node. In the snap mode, this is not possible. Given the specific backend is used by multiple services and the backends need to be aware of the different IP and ports, we can't do it in snap, but we can do it when we enable the DSR mode. All right. So that's the introduction to the idea of DSR mode. Let's talk a little bit about how to implement it and how it will work, right? So we want to continue using a tunnel protocol. We want to continue using Geneve. There is also an option where we're not using any tunneling protocol, but in my scenario, I want to keep using Geneve. And I'm actually going to use, I've already got queue proxy replacement set. I'm going to enable these two fields, load balancing mode DSR and load balancer DSR dispatch equals Geneve. DSR with Geneve is compatible with DSR with Geneve encapsulation. It works either in direct routing or with the Geneve tunneling mode. Unfortunately, it doesn't work with the XLAN encapsulation mode. So that is why we're going to do what we're going to do. So let's go ahead and try that out. Let's see what the difference here is. I'm going to destroy the cluster. Client Cilium, make destroy. Boop. And we'll bring up the cluster again with Geneve and DSR, and then we'll rerun that same set of experiments that we just ran and kind of see what the difference here is. So make file and up should include DSR. So what we're going to do, we're going to do the same thing, right? BPF control plane, Envoy enabled, Gateway API enabled, Hubble UI related enabled. The only thing we're adding is this DSR mode to the load balancer mode, and we're also adding DSR dispatch Geneve. Do our makeup. And then we'll rerun our experiments and we'll see what changes here. Waiting for the load balancer IP pools to be defined. Here comes Cilium. And we're deploying our gateway API resources. All right. Creating all the things. Move my KNS again. KNS. And red. Pods. So there we have our containers are coming up. Okay. Kernel expose deployment echo type load balancer labels color equals red. Kernel get SVC. We got our service temp type load balancer. It's exposing it on port 8080. So let's go ahead and connect to it, right? So curl minus SSL 30010 to 8080 rep. Oh, look at that. The requesting IP is not lost. Let's take a look at this from Hubble's perspective again, because I think that'll be the aha moment for some folks. So let's do Cilium Hubble port forward. We'll do Hubble observe -n tenant red -f. We do our curl. And actually, let's do a curl print node name. So this traffic was attracted to lab worker 3 and lab control plane. Okay, and so we can see from this output that the first connection was made to the lab control plane. There's no worker on lab control plane, right? So it went to overlay, and it basically forwarded via that Geneve header the information necessary to route this traffic to a node where the workload exists, and then it will connect it. And if I scale this up, right? Scale deployment echo replicas 5. So even just then, it took a different host, right? It sent it to the lab worker. And if I run it again, that time it sent it to lab worker 3. That time it sent it to lab worker. That time it sent it to lab worker 2. That time it sent it to lab worker. That time it sent it to lab worker 3, lab worker, and the IP address is never lost. So with the DSR mode, we're able to ensure that when traffic is forwarded, regardless of what the service of type of what the external traffic policy is, the source address is never lost because we're landing the traffic, and instead of snatting out over to the other node, we're actually encapsulating the information necessary in the Geneve header and forwarding that information to the other node and saying, this packet, when it arrived at me, was coming from this source address. And here it is now arriving at you. You can use that very same source address as part of the information that you're passing up, as part of the packet information that you're passing up to the actual pod. So even though I'm always sending my traffic to the lab control plane, it's always finding its way back to the correct, it's always finding its way back to the correct workload, and that source address is never lost. So if you're in a situation where you need to apply that network policy and you need to be able to apply it, apply -f cmp.yaml, and you want that to work every time, it's just important that, and you want to make sure you're getting a good dispersal of workload. Right? Then this is one way to do that, to ensure that you're actually using a mechanism like this. We are going to attract the traffic just like we did last time when we were actually looking at this before with the Cilium BGP routes. Cilium BGP routes. We can see that in the Cilium BGP routes across all of the nodes, I'm still doing that thing where I attract it locally. So any node can terminate it. And once that traffic actually terminates on any one of those nodes, regardless of which one it lands on, we will actually forward that traffic to the correct node or a node where a workload exists. And we'll use Geneve encapsulation to forward the IP information over. So, in summary, if you're going to try to enforce Cilium network policy or Kubernetes network policy, it has nothing to do with Cilium. If you're going to enforce network policy on external sliders and you have a service of type load balancer attracting traffic into the cluster, you do have to kind of consider what happens with that source IP address, because the enforcement wants to take that source IP address into account. And if that source IP address is changed because of the route through the cluster, we have to consider what that looks like. Further, if you want an even dispersal of that traffic, DSR mode by Cilium is a pretty good way to do that, right? Because it means that you can attract that traffic to any node. You're much more resilient in that way. So any one of these nodes could go down. I would still be able to attract the traffic. And I can attract that traffic to any node. I can attract that traffic. Once that traffic lands on that node, I'll make that routing decision about what healthy endpoint to go send it back to. And then once I send it back to that healthy endpoint, I don't lose the source address. So this is actually, in my opinion, really, really cool and really, really good to know. And I hope that you found this educational. And I hope you have the best weekend of your life. And I'll see you all next time. Talk to you later. Bye.